I appreciate you all coming out today to bear witness to research that was done during my sabbatical leave in the spring of 2013. And notice that was quite a while ago. I'll explain why in just a moment it happened that way, but the original plan was to actually go to the University of Sydney. I was looking, polishing off my proposal, and I was proposing to do physics education research at the University of Sydney. This is one of their major buildings in the background here. They do some really cool stuff for introductory physics. Some things that we actually ultimately have adopted here. At the time when I saw some of the things they're doing, buoyancy first semester. Who does buoyancy first semester with fluids? No, it makes perfect sense, and we actually do it here now because of their inspiration. I was also supposed to team teach a medical physics course, which would have been really fun and fit into our biophysics minor. And I was going to evaluate, my contribution was to evaluate something called conceptual survey of fluids, which I developed here. It's in the process actually of going national as part of the survey. And something of very interest to them because they were teaching largely life science. Needless to say, it didn't work out. For one, I did not get the full grade, although, honestly, last sabbatical I had taken prior to that, our home equity line was definitely tapped in in order to pay for things. And so that wasn't unusual. There were family health issues, and perhaps not the ones that you might think of, you might be aware of. I actually, probably because of Lyme disease, was diagnosed with autoimmune disease, rheumatoid arthritis. And it happened big time. That's during that break. And I was glad to be back near our healthcare system in order to get all those things taken care of. Otherwise, I can't imagine what it would have been like in Australia. So I continued to do research, and I'll describe 4 papers that were actually published based on research that was done during that spring and also the following summer. I do wear 2 hats. I do atomic force microscopy, and I'm going to give you a nice little demonstration in a bit and show you the paper that came from that. And some research associated with undergraduates to actually make laboratory activities that have been adopted in our laboratories in order to try to improve our instruction. So I can't go any further with this without acknowledging the person who made this all possible, which is my late wife. She was amazing. She worked in the, she worked in the Ganter lab. Her background is in developmental biology. For those people who know biology, that's kind of like the astrophysics of physics. It's extremely, you have to know a really broad range of subject matters, and she loved her research there. And while I was dealing with my health issues, she was taking care of course, the family and raising 3 wonderful boys. Why didn't I give this presentation afterwards in the fall? She was actually had a recurrence of cancer, which eventually took her life. Completely coincidental. When this date was selected, I said, oh yeah, April 22, Earth Day, that's great. It's also 2 years ago that she passed away, as of today. And I was just a little bit clueless at the time. I didn't think about it, but honestly, there's no better way I can honor her by giving this presentation. She made this all possible, quite frankly. First off, AFM characterization of Leptophyx oshirkai. What does this look like in the background here? Does it look like pollution? When I first saw that picture, that's what came to my mind.
Rusty pollution.
Iron.
Yeah. It's like rusty pollution.
Rusty
like
pollution.
acid
Now this is natural
right
occurring. This is iron seep. There's a lot of iron underwater, and there's this bacteria in there that says, hey, nice, I got all this energy I can extract and live. And all these rusty deposits right there are actually from the sheets, the tubes at which this iron oxidizing bacteria live in. When the tubes are fresh, they actually are bright, vivid orange. And this was done in conjunction with my colleague David Vesenka at Bigelow Laboratories and 2 undergraduates. I'll talk about Kate's work later on as well. This is a scanning electron micrograph of what this looks like. I'm going to turn off the lights over here so you can see things a little bit better. Did I just turn that on? Oh, it
Other
wasn't.
one, the one that says main.
Do you want me to turn off the main lights? Or is,
I think we're fine.
This is okay. So anyways, this picture on my computer looks great. Over here, this data projector is getting old. There's a whole mat of these, they call them sheaths, that are in this picture to the right. And this is the same image, but after staining with a DNA stain. And you can actually see this bright line of bacteria. The majority of the sheaths, well over 90%, are actually empty. They only live in little tiny portions of the entire range over there. And so what I proposed to do with my colleague was to take a look at these using something called the atomic force microscope. And the image to the left is in fact this machine right here. And I'm going to briefly explain how AFM works. I have a nice little demonstration over here that I do with some outreach programs. And basically what you have is a very, very sharp tip attached to a cantilever. So this is a not so sharp tip attached to a really, really, really big cantilever. These things are only about 100 microns long, about the width of a human hair. And the length of this is 10 microns, so a fraction of the width of a hair. And what happens is you have a laser beam that is designed to bounce off the back side. And here, John, you'll want to close your eyes for a minute or two. This is a very, very green, there it is, ooh, first shot. So you can see the spot on the ceiling there, all right? Old school, they would take the AFM tip, they would gently press on the surface until they saw it deflected, and they would say, oh, once we go over something, like this is a thread, did you see how much that moved right then?
Mm-hmm.
There it's going up, there it's going down, okay? Old school, they would actually find that deflection. The fact that you can see such large deflection up there is something due to what they call optical gain. It's the ratio of the path length over there to the length of the cantilever. And the problem with that particular technique actually can be seen right here. I was interested in cutting these sheaths, and so I went into contact mode and just screech went across the surface, and I broke them in half. If you actually want to image them, you want to image in a much more gentle fashion. It's called tapping mode. So this is a bright field image, a bunch of sheaths. Here, stained, you can see that only a few of these sheaths are actually have bacteria in them. And then I'm going to zoom in on this region of space with the AFM. And interestingly enough, 30 microns, that's about as big an area the AFM can see. It's not a very large scan area. I zoom in on this area here, and you can see the regions of where the cells are. These are cells. This is a collapsed sheath, and this is an intact sheath. To an AFMer, we take a look at that and we say, woohoo, we completely understand what's going on. This is a very tall structure. This is lower, and the microsurface is way in the background because we see height by color. Just to show that is indeed a three-dimensional image, we can put this into pseudo 3D, and you can see this tall structure is slightly rotated. It's the same image, but there's the intact sheath, there's the collapsed sheath, and there's the DNA over there. So how does this tapping mode technique work? Well, it's a little bit different. The way it works is, I'm going to adjust this one more time. They actually can get the tip into resonance because there's natural resonance frequencies. Whenever you take a look at a meter stick, you'll notice that there's one frequency at which it wants to vibrate at. So this one also has a resonance frequency. I'm going to turn on the power to this, and I'm going to adjust the laser beams so it's right in the middle. And I crank this down to about 6 hertz, 5 or 6 hertz in that neighborhood, and you can see there's a natural resonance there. The fundamental resonance isn't always a good place to have the imaging done at. Sometimes you want to go to higher resonances, and there's another resonance at around second order, what they call, actually in this case, a third harmonic. You can actually see right there, okay? And what they feed back on is actually damping of the amplitude or changing of the amplitude. And I can't really show this by bringing in contact with a physical sample, and the reason for that is it's very, very tiny, but I do have some magnets here. And as I scan these magnets across over here, take a look at what's happening to the ceiling. Do you see much change taking place right now? There's a little tiny shift, not much. How about this really, really tall magnet right here? Whoa, oh, it got so strong it actually attacked it. A little bit too much. And here's another one, it might get attacked too. And this is actually a problem that they do have with some of the technologies that can actually grab onto it.
So David, the one you're showing us, this is just a model.
Just a model.
That's all that this is. This doesn't.
Yeah. So what they do is
so much bigger. Yeah.
they actually oscillate the tip back and forth. It's a little tiny tip. You saw in the previous image approximately the size of what they look like over here. And this is actually a bright field image I took, and you can see the size of the tip compared to the sample. These are nice big samples. They're optically easily visual, so you can go ahead and navigate and find the sample very quickly in order to do imaging. So I'm doing all this imaging, and I actually worked with the gentleman prior to this for a couple of years, and I didn't really know what we were supposed to solve. And unfortunately, that sometimes happens with AFM imaging for me. I just like, what's going on? You interpret stuff. But a real interesting thing came up, and the images that I'm showing were taken that spring, in dealing with something called motility. How do these suckers get around? Turns out bacteria, majority of them have flagella, little hairs that they spiral around and allows them to move through solution. Sometimes they do it alone, sometimes they actually are in groups, and sometimes they don't even have to worry about that. They're just reproducing. And because they reproduce, they can go ahead and move along the surface. Sorry about that. So it's one of the ways that you can see these things move around. These bacteria live in sheaths. They don't have flagella. They've never been able to see any, not with any electron microscope, not with any other technique. But what I managed to do was I imaged a really, really fresh sheath. Okay, you can actually see it here in this phase image. It's just been created, and then, totally fortuitously, I managed to find some of the bacteria without having any sheath on it whatsoever. And this is very unusual. And I imaged these structures, and if you look closely, you can see them extruding polysaccharides. And so we came up with a model. We looked at a bunch of different possible physical models, not the least of which was the Bernoulli relationship. There's no way there was enough pressure to cause them to move. But the suggestion was actually a pretty simple one, which is these critters extrude polysaccharides. The polysaccharides harden into a sheath. The sheath gets thicker in time. When it gets thicker, there might be a shear force acting on them as they're squeezing out stuff which pushes them forward. It's basically a Newton's third law. That's all that's taking place. And this has actually received quite a few hits for an AFM paper, and was published. This one took the longest time to publish, but the results were all the data that you see up here was collected in 2013.
So they're growing their own means of motility?
Well, they make these sheaths, these tubes that they live in, but it's thought that they're always found at the very front end. There's this other evidence I didn't mention. They're found at the front end of the sheaths. And because they're found at the front ends of the sheaths, is for some odd reason, they're living there, that's where the most nutrients are. And it seemed reasonable. Hey, look, they're extruding this stuff. As the sheath hardens, it can be, as the material pushes against the sheath, it could push them forward. Which is, there's some evidence, other evidence that we have which shows that the way the sheaths grow, they're longer in the parallel direction to the tube axis, which indicates that's the way the material is being laid down. So there's a variety of evidence that we collected through the AFM imaging that suggested that this was a reasonable mechanism.
I know these are super elementary questions, but I'm wondering, is it a coincidence or is it an adaptation?
That's my son, sorry. Hopefully, it's not super critical. Is it an adaptation? I don't know. I mean, we're just making these,
Thanks.
making these arguments based on the evidence that we can see. So that is the AFM part of the presentation. The rest of the talk deals with a variety of undergraduate research projects involving physics education research that I've started, initiated. Some of them were actually initiated, then some of them were, we collected all the primary data at that time. The first one is this work with Beth Whitmore. I don't know if anybody recognizes her. She's currently a graduate student at in Oban Gavench's lab, PhD pharmacy that she's currently working towards. She took my class, my university physics class in 2012, and was interested in doing some research, and I said, oh, I'm on sabbatical, maybe we can do something that would be helpful for our classrooms, which we didn't have very many good IPLS, Introductory Physics for Life Science lab activities at the time. And one thing that was interesting to her was circulatory system. And the question is could we make a model circulatory system that would help the students better understand what takes place physically in the human circulatory system? And you can imagine that this is modeling the aorta, the capillaries, and the vena cava, and that was the idea behind it. And when you let colored liquid flow through here, you can actually see it cruises through these areas, which is exactly what happens with blood coming out of your aorta. But because there's so many capillaries, by the time it gets there, it moves very slowly. And that's important because yeah, oxygen transport.
Right.
Yeah, so it's based on diffusion. You have to slow things down, okay? These little black boxes are pressure sensors, and you actually can model really well how pressure changes as a function from here by the heart all the way to the end on the return path. It drops, and that was really surprising for me. You see these pictures, but if you actually model it and you get this result, that was fascinating. And it was published, peer-reviewed conference proceedings in 2015. Beth actually gave this presentation at the Portland AAPT meeting. Another bit of work that was started at that time, I love doing simulations, and I needed to, while I was laid up for a while there, I needed to do some computer simulations. And I had the student who was a really go-getter, Kate Ruby, and I said, there's this very interesting problem that I've been wanting to work on. Would you like to see if you can help me with it, involving a representation for momentum that was a little bit different than the traditional ones. The traditional momentum representations are these vectors shown on top here. They're really kind of boring, not terribly transparent, but the idea is that if you add up the total momentum before a collision, this is two particle collisions, they have to equal the momentum after a collision, even though your momentum vector will completely change. The reason why I didn't find this fairly useful for the undergraduates is that you can't tell anything about their masses, you can't tell anything about their velocities, and those are things that are really of interest. Whereas if you represent it like this, where mass is along that axis, velocity is along that axis, mass times velocity is momentum. The area represents momentum. Okay? This is a large positive momentum. This is a larger negative momentum. This is a smaller, this is a large negative momentum afterwards, and this is a smaller positive momentum. And so this was another way to map it out. And the cool thing about GeoGebra, I actually had James Quinlan, a colleague of mine, help me originally do this project in MathGet. And that was hard. That was really, really hard. Whereas this one took no time at all to program. This was fast, and this is dynamic. And what I mean by that is, let's go ahead and change mass 1. Mass 1 is up here. Let's make it bigger. Whoa! You can see what happens when you make that bigger. Let's go ahead and change the velocity. Woohoo! You can see how everything else is going to change. All this is very dynamic. You can take a look at other types of situations. This is for elastic collisions. If you have inelastic, completely inelastic collisions, interesting stuff happens. Okay, your final velocities are going to be constant because the two things stick together. Okay, and then there was one thing that is often missed, which is explosions. What happens when two things blow apart? And we'll go ahead and show what happens when two things blow apart and have initial velocity of 0. They're going to just be, the masses are going to break off into opposite directions. So it was really kind of fun. Very, very easy to do, and Kate deserves a lot of credit for pushing this through. I helped her with a lot of the programming, but we did get it done. There's a nice, and it's used by our students right now routinely, and it's published in North American GeoGebra Journal. Last project that I'm going to present here today is something that you would have thought was pretty obvious, but how can we do sound expenses really, experiments really inexpensively? And the answer is earbuds. Okay, you can actually, this is freeware called Audacity. Audacity will allow you to generate tones. Here it's generating 2 tones. This is the internal speaker measurements of something called the beat frequency. One of these microphones is generating 1,000 hertz tone. The other one is 1,001 hertz, 1,002 hertz, 1,003 hertz, 1,004 hertz, and you can see the beats that are generated from that. Why is this one not canceling like the internal microphone? Can you see the microphone is right here? What do we know about sound? When you make a here and you go ahead to the end of the parking lot, it'll sound much more quiet. That's because the amplitude decreases with how far you are from the source. And so one of these has got a larger amplitude than the other, and that's why there's not complete cancellation. So anyways, this is kind of fun. Another activity that we did was 2-speaker interference. I want, once again, with earbuds. The computer microphone's right here, and just sweep it across, and you can actually see constructive and destructive interference, which is really, really cool. Probably one of my favorite ones, which I'll demonstrate in a little bit, is this one right here, which is, you can swing these around with a constant tone, and you can hear the Doppler shift, which is really, really fun. This is also using Audacity. And the Audacity can give you the frequency shift. It can tell you how much the frequency changes through the center peak. The slope here is related to the central peak frequency times 2 divided by the speed of sound. And that's a pretty accurate representation. I'll go ahead and demonstrate this to you in just a moment. What really got me going on this particular activity actually was this laboratory, which we routinely do. We take a graduated cylinder, and we take a tube, and we put it inside here, and we put these microphone, or actually tuning forks up to it, and we listen for the resonances, okay? And the tuning forks have challenges. They need to be constantly vibrated or whacked on your head or whatever it is that you use in order to keep things going. Whereas microphone can just go nonstop, and it can also be much quieter, and it can also be much higher frequency, which is really good for the kids. You don't have to run the amplitude so loud. There are some challenges with these small tubes, which I'll show you in just a second. But the thing that I found interesting, which is also discovered back at that time, is if you take a look at these data points, this is for a quarter wavelength effect. Quarter wavelength resonance means that the frequency of the wave exactly is 1/4 of a total wavelength right here. Certain kinds of musical instruments, including the meter stick right there when it whacked at one end, has this kind of behavior. Other types of musical instruments have lambda wavelength over 2 effects. So for wavelength over 2 effects, you actually get a whole bunch of pipes with different lengths. and you just listen for the resonances. The wavelength over 4 effect has a speed of sound that is related to the wavelength by about 1/4. This slope is about 1/4 the speed of sound. This slope ends up being about 1/2 the speed of sound. The thing that I want to point out is the green line, the blue line, those are exact solutions based on the speed of sound at that day. Notice the error bars here, guys? They're not superimposing with the exact solution. What's that all about? And so we started to explore, this has never been published, but it's something that I'm thinking about looking at in the future. What happens when you change your tubes? So I'm going to go now into a mode where I'm going to break out here and show you a couple of these demonstrations that I do using Audacity. Bear with me. I've given myself plenty of time right now to try to show you these things. So this is what Audacity looks like. And I have a variety of different sounds set up right now. The first one I'm going to show you is the Doppler shift. Wow, 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 wow. And that Doppler shift is a function of how fast you spin it around. The faster you spin it around, the bigger the Doppler shift, okay? Because it's bigger or the smaller it is going towards you. Here's another example that I showed you previously. This one is going to be, I'm going to crank it up a little bit. And we're going to listen for resonances right here. Can you hear that transition taking place there? That's what that's the fundamental. That's the second. That's n equals 3. Actually, n equals 3 in terms of harmonics. Okay. This experiment is not quite as nice in terms of you actually get, with these bigger diameter tubes, it actually sounds louder instead of actually having a little bit of cancellation there. Not exactly sure why that happens. That's another interesting area of research. But it's something that I'd like to explore. One of the things that we have done with these, which is really fun, I'm going to put this into mute and turn this on. I want you to listen very, very carefully to the sound that this is going to make as we run this through what's called a frequency sweep. Okay? Tell me what, first of all, you're going to listen to it straight out. No, not going through tube. So it just went in 10 seconds through 200 hertz to 2000 hertz. Now listen to it, and afterwards let's discuss what we just heard. Did you guys hear anything different at all?
Seemed like it went higher.
One more time. It's not obvious, but it's actually getting a little bit louder, and then quieter, and then louder, and then quieter as it actually goes through the resonances. Why doesn't our ear pick that up? You get a cookie if you can answer that question. You got one anyway. Why doesn't it pick it up? Same thing actually with your eyes too. It's the kind of detector they are. What's that?
Because we're not expecting?
Well,
making it pretty
our eyes and ears are not linear detectors. They're logarithmic detectors. And so small changes like that don't appear as clearly. However, you go ahead and put this into a microphone, which is a linear detector, and guess what you hear? You get this effect. It actually can pick up these big peaks, okay, and there are specific frequencies. What do you know about those frequencies peaks? Are they staggered? Are they all about equally spaced? They look equally spaced, okay? Save for some funny business down here and this stuff right here, which I have no idea what the heck that is. But yeah, they're pretty equally spaced all the way across. Okay, why? Well, they're actual integrals of half wavelengths. That's exactly why they should be for that particular length of the tube. Now, if you run it through one of these really funky ones, and these were actually made at a on 3D printing, 20 centimeters long, exact same length, exact same diameter at the end. This is what you get. What do you know about the spacing here compared to the spacing of the red peaks? Closer together, farther apart? Closer together. What the heck? What's that all about? If you go ahead and plot the frequency as a function of the harmonic, okay, you get this plot. That slope is exactly where we'd expect for the speed of sound at 343 meters per second. Okay, it should come out to about 805. Okay. This one is 35% smaller. We've slowed down sound by putting it through a bumpy medium. I would not have ever observed this result before if we hadn't been using some crazy tubes. There's actually a big long tube in the background there. Big corrugated pipe. Anytime you get corrugated pipe, funky stuff happens. A colleague of Bradley Moser's suggested, well, you can treat it kind of like an index of refraction. When you send light through an optically dense medium, it slows down. It slows down because it has to interact with the matter in the medium, re-irradiate, go to the next particle, re-irradiate, go to the next particle. So there's a time delay. It slows down. Something like that could be envisioned taking place here. I wouldn't argue that it's necessary. I don't think you could justify that the density of the air is changing, although there's definitely some weird stuff taking place in there. And I would really like to explore that more in the future. I think it's really super interesting. So, future sabbatical research, this is one area that could be fun. Another area in the past, I worked on quadruplex DNA. This is an example of quadruplex DNA here. It's made by guanine quartets, and that was my big international exposure. I did a lot of research on this and did AFM imaging. These are AFM images here. DNA origami is this cool thing where you can take oligonucleotide sequences, and if you're very clever about it and you just find the exact right lengths, they will make all types of cool structures because they self-assemble, and that's just the way they appear. And so these are what they, this particular group, and this is a group in Japan, was interested in doing. They made this platform on the outside, and then they had these specifically sequences that make a cross in the very center in order to, they were interested in understanding more about the particular structure in the very center here, which was kind of cool. And I have a colleague in Vienna, Germany, who's done DNA origami. I don't know if he's interested specifically. Lastly, one of the physics education research things I was doing this past summer, I went to a Gordon conference and spoke a little bit about energy work. And I met this guy at, who would have thunk that there was this thing called the National Renewable Energy Lab. Do you guys ever heard of that? Where's it located, Pam?
It's out west somewhere.
Yep, in Colorado.
Colorado, yeah.
So
It's a really
I saw this and I said, you know, and he's showing this guy right here, gave a presentation at that talk, and he does a lot of imaging, electron microscopy, atomic force microscopy, and stuff like that. And I thought, oh, that would be so cool, because I've been really interested in this energy and environment course. And they do have programs that allow you to apply for year-long research possibilities. He does, so this is some of his imaging that he does. He actually takes a look at the biofuels and how they behave in order to get optimal combustion and things like that.
Is that a private lab or a public?
This is a public, yeah, national renewable energy.
Oh, so it's federal. Okay.
Yeah, it's a federal lab, just outside Golden. And he does a lot of computer simulations, and frankly, for me, that would be actually a big help, having a better computer simulation experiences. So I took basically 6 or 7 months of research, and I squashed it down into just a little over 37 minutes. If you've got any questions, I'm more than happy to answer them about any of the stuff that I've done.
So were you able to put a lot of these things into your intro physics class, or is this more for upper level students?
Oh, I'm glad you brought that up. These are actually, I've got a couple instructors here, and they'll tell you that we're using the earbuds, or I persuaded them to use the earbuds. Honestly, one of the reasons why I was really interested in the earbuds is because, you know, we have this thing called snow that periodically happens and periodically cancel classes. A lot of these activities, kids have earbuds and computers. You know, if we happen to have a snow day, and the students are alerted in advance, like, snow day does not mean you're going to be excused from doing stuff. We can have these labs, they can do them themselves, because they're very, very cheap. And I've been working on a lot of these super inexpensive type of laboratory activities, specifically in mind to have makeup opportunities, and also makeup opportunities as well. And earbuds, and there's just so many different things you can do with sound. And been working on a lot of these inexpensive ones. In fact, there's a group in Czechoslovakia that a colleague of mine mentioned who said, oh, they'd be super interested in these inexpensive lab activities, because in large parts of the world, having the kinds of equipment that I showed you over here previously, that's going to be difficult to get a hold of. But these kinds of things are really easy to do. People have them all over the place. So.
I have a question about the momentum simulation.
Sure.
Have you explored how to make that work with two-dimensional collisions? Does GeoGebra do 3D? Because you would have one axis for the mass, and then you need two for the velocity.
Yeah, you could
you do
easily make it go into multiple dimensions. In fact, yeah, the GeoGebra allows you to do three-dimensional presentation. I was actually thinking of using the third dimension not to do y direction, for example, which you certainly could do. I was actually thinking about the third dimension to do kinetic energy, to show the difference between what happens before and after collisions. I had started to work on that, but you could easily extract it, because GeoGebra can easily do 3D.
U&E is the main, so GeoGebra kind of like diffuses its innovation through making a place in each state that's like the center for GeoGebra education, and U&E is the main GeoGebra center.
Other questions? Please.
What are the next AFM experiments that you want to do?
Oh, I want to get to, I'm actually going to try to get with my students in the biophysics course this semester to image some of the GWIR DNA that my colleague sent me from University of St. Thomas University of St. Thomas, the one in Minnesota.
University of.
He's got some beautiful GWIR DNA that he made, and I really like to see. There's a major groove, minor groove, and your traditional duplex DNA, which depends upon hydration conditions. If it's really dry, when does it flip? When does it become from right-handed to left-handed? There's it can change helical conformation depending upon hydration levels. Anyways, you can see that with our machine, which is something I've always wanted to do. And the quadruplex DNA is really bizarre because it's got this, it doesn't have a major groove and minor groove, it just has one groove. And it would be really cool if we could see that. Because apparently there are also some interesting conformational changes that take place with it as well. There's a paper published in Science. Damn it! That would have been really cool to have done first. But yeah, that's where I see going next. And then, of course, you've got a lot of wonderful stuff that I'd love to take a look at.
I'm in your stuff.
Yeah,
I know
or for me, yeah, I'd like to try to get going on that. I also have a final demonstration here that was inspired by a YouTube video. And it was this crazy picture of this water wave sinusoidal wave out in space, and I remember Bradley and I were looking at this like, how the heck did they do that? How the heck did they do that? And when they changed the frequency, they have a speaker, and they've got a tube, and the water's coming out of the tube, and I'm going to be shooting it over here, making a big mess in just a moment. But I'm going to encourage you to come over there and take your cell phones. Does anybody have a ticker that will have problems with strobe light? Because I do have a 30 hertz strobe light I'm going to be using. Anyways, I noticed that they made the water go forward and backwards, and I'm like, oh, I know what they did. This is in bright daylight that they managed to get this sinusoid without using a strobe light. And the answer is they were using an old cinematographic camera, which runs at 24 frames per second. Each frame is at stop action, ching, 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 ching. If you go ahead and set your speaker up at 24, you get a perfect sine wave, okay? And if you adjust your speaker a little bit above or a little bit below, you can make it appear to run forward and backwards. And we don't, I tried to do this with the cell phones. It doesn't work, sorry guys. However, because they do run at 120 frames per second or 60 frames per second, but I was discussing this with John. There's some kind of digitization that do, the way they do digitization, their codec smooth things over. Yeah, so you can't, there's smoothing that taking place, so you can't catch it just by setting this up at 60 hertz if you have an old phone like mine, or 120 hertz. However, I do have this set up over here. I'm going to turn on the water. It's going to take just a moment or two. You may hear me swearing a little bit. Oh yeah. The big black blob across the screen is because of the frame rate of the camera. Going backwards. Going forwards. Now let's see if we can get exactly the frame rate of the camera. Yep, can't do it. It's 20.998, and so it's close to 30 seconds. Oh well. But it does make a very pretty sine wave. Next time it goes through, I'm going to show you what happens when you stick your finger in the beam. When you stick it in there, you will find that you'll get a the water will actually go all over the place. You can see there is actually water at that spot.